in our design is 30 degrees. Now, if you remember, let me just draw this because this is where I had a bone of contention with the class, but we can help resolve it. If you remember, it was very critical for us to have a proper diagram. Okay, so that's what I want to try and draw today so that it's visible. Okay. In our class, we said that the desired that, and we obtained this, so I will not show how to obtain it again. We had obtained a point, which we had said was our desired point. And let's call this point P. And we figured that the point should be somewhere at J2 root 3. And this was the location of one of the poles. There was a pole at the origin and another pole at -2. Okay, another pole at -2. So we had a pole at the origin. We call it, let's just call it O. And then this was point -2. And so that point corresponds to that pole. Okay. Now, this is where the work begins. If we are to obtain the pole, remember our desire is to have C of S equals to K S plus Z over S plus P. So we need to know that for a lead compensator, we must have a 0 and a pole in that order. But where do we place them on our complex plane? So to place them correctly, what we have to do is, and this is the procedure. I remember yesterday Ismail asked if how I decided on the angles. This is basically the procedure that you will use for all the questions that I give you for the lead compensator. So the first thing, because the desired point will always be on this segment, so it's going to be that point P. The first thing I said was you have to draw a straight line. Please remember that. We draw a straight line like that, okay? And then, let me just actually even make it better because today I want everything to look neat and convincing. So if you have a straight line there, to that point, our point which is here, okay? Then what is expected of you is to also have another straight line to this point here, to the origin. You must draw that. You need to have another point to the origin, another straight line to the origin. Okay, so let me try that again so that it looks neat. Now, because we have those points, it is very clear that in yesterday's class, the rule that I told you, or the design technique that I said, is that if we call this point A, then we must get, we know there's an angle APO, but we have to subtend this angle APO. So what we must have is another angle. We must draw a line. Let me use a different, let me use some point here to denote. I'm drawing a point that is directly, dividing or subtending this angle, sorry. And this is where it gets tough, but we have to do it. And it's very important that we do it correct. So, good. So let's call this point B. So remember, these were the only two poles that we had for the plant system. We have not added the pole for the compensation. But this kind of geometry is very critical in determining the locations of our pole and zeros for the design. And you'll see that in a short while. So you can clearly see from here that this, if we are saying that we are dividing this, the angle A APB should be equal to angle BPO. So the angle APB should also be equal to angle BPO. Okay, and those are just half, because we are dividing APO into two equal portions. So we're just subtending it equally. So we have the angle APB should be equal to angle BPO, which is half angle APO. So this statement here is the one that is like the key to unlock the positions of our poles and zeros. I know I have not indicated them yet, but I'm about to do that. So always you will see that when I refer to a desired location or a desired point like this, or point P, you will always be required to draw this before you indicate the pole and the zeros, or the pole location and the zero location. So before I even go there, we can actually see that this angle, because now it's like we are saying the triangle BPO is an equilateral triangle. That is exactly the essence of doing that. Equilateral triangle. Okay? The triangle BPO is an equilateral triangle. So that means, therefore, that this angle here is 60 degrees, and this is going to be standard for all the cases that we are going to deal with. It is the only way we are able to determine those points. Okay, so that means this angle is 60 and the other angle is also 60 degrees. Then now we can put up the location of our pole and zero. Remember, for the lead compensator, the zero is at that point and the pole is at that point. Now, the design procedure here is, we know that the pole and the zero for our design should be on the left side of the poles of the plant. So the poles of the plant is at the origin and at -2. So we take that our design pole and our design zero, the one we are adding, should fall to the left of that. So in order to obtain this accurately, we have to place a pole somewhere, a zero somewhere here. Let's say a zero is right here, the one that we are adding in our design, and then we place the pole somewhere here. That is the only way. So you see, we've added the zero and the pole that is required. But notice how I have added them. I've added them such that we assume that this point, if we draw them to the, if we also just draw a line that connects them to the desired point, today I think it's clearer. So notice we've added our pole and zero, but we are assuming that the point B is cutting the pole and the zero at the middle point, such that this is minus Z, because it's the position of our zero, and this is minus P, which is the position of our pole. Okay? Now, we are saying, so if this point here, let's call this point here point C, the one at the pole is point C, and the one at the zero is point D. Okay? I need to use that part. So, okay, we'll call this point C. So this would be point C. Let's call this point C and this point D. We are saying that for us, because in order for us to obtain the position of the pole and the zero, we must indicate that the point C, let me say the angle CPB should be equal to the angle BPD. That's very important. Meaning, and we had indicated that from here, that our lead angle is 30 degrees. So basically what we are saying, the angle between the pole and the zero is 30 degrees. This angle here, between the pole and the zero is 30 degrees. That angle is 30 degrees. Alternatively, what we are saying is, because we divided point B is dividing the pole and the zero at the middle point, then this angle is 15 degrees and the other one is also 15 degrees, so that the total is 30 degrees, because point B is subtending point C and point D in the middle, right in the middle. That way, ladies and gentlemen, is the only way we'll be able to get the angle at point at the zero and the angle at the pole, meaning the angle at point D and the angle at point C. Why? Because we know this is 90 degrees. Okay, so this is also 90 degrees. So we can call this angle here. This angle can be called theta Z. And this angle here can be called theta P. Now, if I asked you to obtain for me the angle theta Z, for example, it should be easy, because now you see you have the angle here, which is 15, and then the angle here, which is 60. So if I subtract them from 180, then I'll be able to get this angle here. This angle, I'll be able to get it. And so then I can subtract that from 180 again, so that I get the angle theta Z. So from the diagram, we can actually say, because our angle deficiency is 30 degrees, to get theta, or let me use a different marker, to get the angle contributed by the zero, we get 180 degrees minus, I'm subtracting all the angles within the triangle BPD, all the angles within the triangle BPD. And so that is minus 180 minus 60 minus 15. And that gives me 75 degrees. And for the pole, we do exactly the same thing. The pole, we are looking for theta P. And so we know that up here we have 15 degrees. Down here, because this is 60, this clearly is 120. That is 120. This angle here should be 120, because this is 60. So this is 15. So we are going to have 180 degrees minus 120 degrees minus, or 120, sorry, 120 plus 15. And then I find my 45 degrees. Okay, so now that we have the angle at theta Z and theta P, then we now need to obtain the location minus Z and minus P. Those locations, I had given you the formula in the previous class, so it should be easy, and you just use trigonometry. So we know that tan theta Z should be equal to 2 root 3, which is the opposite, over the adjacent, which is Z minus 2. And so if you substitute, you'll see that we can say tan 75 degrees. The tangent of 75 degrees should be equal to 2 root 3 over Z minus 2. And if you solve this, then Z should be equal to 2.93, meaning this location here is minus 2.93, minus 2.93. Then you do that with the pole. So tan theta P should be equal to 2 root 3. The adjacent is P minus 2. And therefore we'll have the tangent of 45 degrees should be equal to 2 root 3 over P minus 2. Solve that, and P equals to 5.46. So this point here is minus 5.46, minus 5.46. So because we now have the pole and the zero location, then now we can use our equation as usual and say that the lead, remember, the lead transfer function should be S plus Z, we had said, over S plus P. And that therefore should be equal to K S plus 2.93 over S plus 5.46. That is how it should be. Okay. In a nutshell, what we are saying in our design, what we have done is this. We have done this. So basically, this was the plant. I think it was 4 over S into S plus 2, if I remember. So, and then our controller now should be K S plus 2.93 over S plus 5.46. So basically, this is our design. That is our own design to make sure that we meet the specifications that were asked for, where the undamped natural frequency and the coefficient, the damping coefficient was provided. So to meet those, because I don't have the question here, this is how you are expected to design this. But now notice there's this unknown, which is the K. So the K can be easily obtained. So we can indicate that to find K, to find K, it's a very easy thing. I told you we use to find the gain K, we utilize the magnitude condition. The magnitude condition. The magnitude condition. For those who have forgotten, we had said that the magnitude condition says that the magnitude of that function should give us 1. Okay? Therefore, we can get K out of here, meaning K should be equal to 1 over G of S, H of S magnitude. Okay? So then we can obtain K. In our case, remember, in our case, our G of S is now a combination of these two, so that we have G of S combined with the controller aspect. Okay? G was the plant, this was the plant, and then this was the controller that we have designed. So if we combine them in our equation, then we are going to have, because the plant was 4 over S into S plus 2, and the controller is K S plus 2.93 over S plus 5.46, like that. Okay, so basically we can just say, we can write it properly and say it is, we have K, and then we have 4 into S plus 2.93 over S into S plus 2, S plus 5.46. So to get the magnitude K, what we have to do, because this is our function it's this function here. So to get the magnitude K, we'll just have 1 over the magnitude, 1 over the magnitude of 4 into S plus 2.93 over S into S plus 2, S plus 5.46, like that. And we make S, remember, please remember, the desired point was provided here. The desired point S, this point S, is minus 2 plus J2 root 3. That's the desired point, meaning that's where we need the root locus to pass. So it is minus 2 plus J2 root 3. So we have to substitute this S. So we have to substitute it with minus 2 plus J plus J2 root 3. And therefore, when we get that, it should be equal to 1. Oh, wait, what am I doing? I've already, sorry. Okay. So when you solve this, you should have 1 over, so you're substituting for s, where there's s, you substitute it with minus 2 plus j2 root 3. So you can solve that using your calculators, and you find, because I did it last night, 2 plus 1, 2.11 plus j 0.0002. And therefore, from there, you can get k as the same as, because it's magnitude, you're actually getting this magnitude. So you'll square and then you get the square root, you'll find 1 over 0.211. You can actually see that the imaginary term has a lot of zeros, so it's almost 0. It's not going to affect. So if you square 0.22 and then you get its square root, you still get 0.211, the same thing. And this gives you 4.7. So this becomes your gain. So that becomes the gain if asked for. You can provide that. Okay. Now, this you should have done in control systems, and I want to believe you did, because you might also be asked for it, and that is, you can be asked to obtain the, this is very important, the error constant, or what is called the step error constant. So these ones are easy to obtain because there's a formula. It's KP. It's like the proportional constant. Yeah, some books will call this the proportional constant. Because if you remember, when you are doing controllers, you have the proportional constant, the derivative constant, and and you also have the integral constant. Now remember, we mentioned that basically when you're using a lead compensator, then we are actually using proportional plus a derivative. So Kp in itself is given, you take limits as s tends to 0. This is a formula of g of s, c of s. So g of s, c of s is here. So this is the same as limits as s tends to 0 of 4 over s into s plus 2. And the other one, I think it's s plus 9. S plus 9 what? 9. S plus, sorry. S plus 2.93 over S plus 5.46. So if you try and get the limits, meaning if you try and make S equals to 0, you can actually see that this point, there's S at the origin here. So if you make this go to 0, then the whole denominator goes to 0. If the whole denominator goes to 0, then it means that the term goes to infinity, okay? And the other term you can be asked for is what is called the ramp error constant. The ramp error constant. Some books will call this, because you know what a ramp function is, it's a velocity constant. I think this should be position constant, not proportional, position constant. Anyway, so the velocity constant here should be equal, you take your limits, s tends to 0 of s, g of s, c of s. This was from your 4th year controls. And so in that case, if you substitute it exactly in our equation, because there's an s here, you will be having something like this, limits as s tends to 0 of s, and then now we add 4 over s into s plus 2, and then s plus 2.93 over s plus 5.46. So when we have it like this, you can see that this s will cancel on this s, and if s is 0, then this point will have 4 over 2. So here we'll have 4 over 2, and then here we'll have 2.93 over 5.46 because S tends to 0, infinitesimally small. So therefore, you end up with something like 5, because now we'll have 2. So we'll be having 2 times 2.93. That's almost 6 over 5.46. Okay. So what you will have is about 5.02. Okay. So that is the velocity constant. Now, you may or may not be asked about this, but what I'm interested in is the values that I just gave you, and that is in getting the position of the 0 and the pole, the design itself. This is the critical part where you're supposed to come up with these values, the design. And once you do that, then you are home and dry. Very, very important. So I hope this will make sense. And so for me to make sure that at least it sinks in, and a lot of students will probably now use this example to learn at a later stage, I want to give you an example that was in the last year's exam, and then I solve it, and then maybe we have in the next 30 minutes, see if we can solve the problem. So now the question is, so let's do another example. Please note this was in the exam, so you have to note it down, or you would have to look for the past paper. So it indicates, the question is, consider a unity feedback control system with an open loop transfer function. That's in full. I'm just trying to shorten it because of time. The open loop transfer function is given by 10 over s squared plus 4s plus 5. So they say design a lead compensator, they're calling it GC of S, so that the dominant closed loop poles have a damping ratio, given by 0.6, and the undamped natural frequency omega n, given by 3 rads per second. Okay, so that's the question. Very important. So that was in last year's exam. It's just part of the question. There are other parts. This was part B of the question. So there are other parts that come before that, and then there's part C. So we have not done those in class. I'm only doing part B because it's relevant to what we have done so far. I told you I will test you on both the lead compensator, the lag compensator, and the lead lag compensator. So you have to do both of them. Now, before I forget, please, I just want to remind you, remember, in this equation, in our solution here, please, this is very critical. I need you to plot or sketch the root locus again. If you sketch the root locus of this only, remember, when we sketched the root locus of that, we had at 0 and at -2. And so the root locus was just like a straight line cutting between those two poles. But if you now sketch the root locus when you combine these two, when you now have an extra 0 and an extra pole, then your root locus is going to change, because now the root locus is going to be like this. So now we have the pole and the one for the plant, and then now we have a 0, and another pole. Okay, each one of them, you know, at their position. So like this one is at 0, this is -2, this is minus 2.93, and this is now at minus 5.46. So you'll know that there'll be a root locus here, and there'll be a root locus here. So this one, you'll see, just go in there, but now it will not look, it will not be a straight line. I told you that the 0 always tends to pull the root locus to itself. So the direction of the root locus will change, not significantly, but at least if you plot that root locus, you will see that it will be something like this. Okay, so remember we had said that the zeros always pull the root locus to the left of the to the left half plane. So you can see that initially, before the design, the plant system had a root locus that was closer to the imaginary line. But because we have introduced in our design a 0 and a pole, the root locus has now changed and it has now moved to the left. But please remember that that point that we had is still now, the point we had -2 plus j2 root 3 falls within the root locus. That point falls within the root locus. Okay, initially the point was outside the root locus, but because we have designed it, we have now forced that point to fall within the root locus. So the root locus has changed. So that's why we say that the design involves reshaping the root locus. Originally, the root locus was a straight line between two poles, but we introduced a pole and a 0, which then changed the shape of the root locus. So this is what we have. It increases stability, because now you can see that the root locus is way, because this is 0 and this is -2. The root locus is to the left of -2, meaning it is more to the left half plane. So ensuring that the system remains stable. That's very important. So, but after design, you should always plot the root locus to see the effect of the shape of that root locus. You can see that by adding this design controller, we have a different setup on our root locus, because we've compensated for the instabilities and stuff and the other performance criteria. So anyway, let me start you off on this, because I would also like to challenge you to go and do this on your own, but let me start you off so that you are on the right track. Okay, so now here we do it exactly the same way we did it last time. I'll just try and lead you to a point where then I'll leave you to complete it on your own, because that's how I'll know that you have been following, and then it will make our work as easy as possible. Okay, so let's quickly find a solution to this. Solution. Okay, I'll not complete the solution, but where I leave it, you'll continue from there, and then I'll look at it in the next class as we start with the lag compensation. Now, the critical point here that we need to note is this: we are given a similar transfer function like we had, so we can actually rewrite that transfer function so that we have g of s. Let me just put it. We can have, we factorize it, because we want to know the locations of the poles and zeros. So 145, that transfer function in the denominator, I mean that polynomial in the denominator, if you factorize it, you should get s plus, get the roots. That's what I'm trying to say. We need to get the roots. S plus 2 plus j, and s plus 2 minus j. So we know where the location of the poles are. Remember, this is for the plant system. So here we have not done anything yet. That is just for the plant system. So from there, we need to get the closed loop transfer function. The closed, because we need to know the poles of that. So for the closed loop transfer function, we have If you get the closed loop transfer function of this, it's like 10 over this. So it's going to be, what we're trying to say, you're getting G of S over 1 plus G of S, H of S. And if you do that, we should get 10 over S squared plus 4S plus 15 plus 4S plus 15. Okay? Then now you compare, because we know that for a closed loop transfer function, the typical representation is S squared plus 2 omega ns plus omega n squared. But now we have S squared plus 4S plus 15. So if we compare this, you can see that omega n should be equal to root 15 radians per second. Root 15 is quickly is 3.87 radians per second. Okay, then the damping ratio should be 2 over root 15, which then is simply 0.52. Okay, now meaning, because remember this was the plant, we converted it to a closed loop transfer function, then obtained its undamped natural frequency and also obtained the damping ratio. So our system as it is has this undamped natural frequency and also has this damping ratio. Okay, I think the damping ratio here is also rads per second. So this is what the system is without compensation. That is the performance of your system without compensation. But we have the design specifications that we are required to obtain. The design specifications. And what are our design specifications? It's very simple. It's indicated. Sorry. Sorry. Okay, so the design that we have is we need to have, let me indicate it using a different marker. The undamped natural frequency should be 3 radians per second from the equation that we had, and the damping coefficient is 0.6. Okay, it's 0.6. So you can compare. Your system without compensation has 3.87 frequency, natural frequency, but you are required to reduce that to 3. Our system before compensation has 0.52 damping ratio. We are required to increase it to 0.6. How do we do that? Simple. This translates to this, if we are just trying to use S squared plus 2 omega ns plus omega n squared. So this if I use these parameters, it translates to having our system as S squared plus 2 multiplied by 3 multiplied by 0.6. So that should be 3.6 S. This is squared, so plus 9. So in short, originally your plant system has this denominator polynomial, but we are required to change it to this form so that it's on that form. Now, which means we need to get the roots of this. So if you obtain the roots of this using your calculators, we should get that the roots of this equals to minus 1.8 plus or minus J 2.4. So this is what we refer to as the desired specifications, or the design that we have to do. So this is what, these are the desired specs. This is what we need in our plots. Okay, that's very critical. That's what we need to achieve. So the way to do that is to plot so that we see where is our desired point. Then we obtain the angle of deficiency or the angle contributed by our pole and zero. And then we proceed from there. Okay. So let me quickly rush you through that and then you will solve it for yourself. So if we draw, and this is where the drawing is going to help a lot. If we draw the positions as indicated there, originally we are told that we have these 2 points. Originally, we have minus 2, what are our roots? Minus 2 plus j and minus 2 minus j. So we have this point here, minus 2. So there are these 2 poles originally. We have not compensated yet. The poles are imaginary. So originally, we have those 2 poles. And this location here, call this J1. This is minus J1. Okay? That is the location. Originally. Okay? But we are desired to have our pole at minus 1.8 and J2.4. So, the space, I lack space, but let's see. I lack space, but we can improve it. So, let's say this is the point that they want, J2.4. And it should be at the point, this is point minus 1.8, closer to minus 2. So it means that the desired location should be minus 1.8, J2.4. That is our desired location. You can see that. See, this corresponds to this line here. And this is the minus 2.4. So this is the desired pole location for us to obtain these specifications that we are given. This is where, so the pole needs to move from this point and come here. And this one should also move from this point and come to the one that's the conjugate of that. Because remember, it is minus 1.8 plus or minus J2.4. Meaning typically another point lies down here in the conjugate form, but we don't use it in our analysis because we just use one desired point. So this is our point P that we need to analyze from. So how do we do that? We need to obtain the angle that is going to be contributed by our pole and zero, the angle of contribution. Okay, to do that, I told you, you have to plot a line between all the poles and zeros that exist. So you have to draw a line that meets, let me use green. I can draw a line that goes there. This one also, you must have another line that comes to this one down here, like that. Okay, so then you have this angle here, theta1, and then you have this angle here. That angle there, theta2. Very important. Okay, it's tight, but you can see it. So I told you that the quickest way to obtain the angle, sometimes we call it the angle of deficiency, but to maintain our standards, to maintain our standards, let me just use, we had said we are calling it theta lead. We know it is theta z minus theta p, and it should be greater than 0. Okay, and I told you to get it, we subtract all the angles from 180 degrees. So we'll have 180 degrees minus, in this case, theta1 minus theta2. That will give us the angle. Remember, we are subtracting because these are poles. We have 2 poles there. So we are subtracting those. So we have 180. Okay. Let me write it properly. So we have 180 degrees minus theta1 should be the inverse tan of the opposite. So the opposite is 2.4 plus 1. So that's 3.4 over the adjacent. Remember, it's at minus 1.8. So the adjacent is 0.2 minus the inverse tan The opposite for this one is just between 1 and 2.4, you have 1.4. The adjacent is 0.2. So you solve this and you find that your angle comes to 11.5 degrees. 11.5 degrees, meaning the angle that is going to be contributed by your zeros, what we can also call phi or theta lead, is going to be 11.5 degrees. So now we want to obtain, notice, don't use your own notation. They have indicated here the lead compensator is GC of S. So if it's GC of S, then we can say GC of S should be equal to K S plus Z over S plus P. Okay. Then now I have to draw this properly so that I can get those angles for you. And what we have just done today. So again, you can decide that to draw this is where you really need to be careful. So again, let me start you off on the drawing, then I'll let you go now and complete it. Because once I have shown you how to draw it, we only have about 5 minutes to go or so. So because I may not even include the poles here because they're not going to affect our calculations. I'm only interested in the point, the desired point. Remember I told you. So the desired point should be at 1.8. So let's say this is 1.8 and this is J 2.4. Okay, that's J 2.4. So the desired point is somewhere here. We're just drawing it again. So this is our desired point. Now, I told you, and this is very critical, please remember that. The first thing that you need to do, because we have determined our desired point to be at minus 1.8 and J 2.4. The first thing we need to do before we indicate the location of the zero and the poles is to draw a straight line like that passes through our desired point like that. Okay? Once you have that straight line, we have that A, P, O. You have to draw another straight line. So you've got this straight line here like that, but then you also have another straight line that connects this angle. So that always we have, and then you subtend equally. So you divide this angle equally. We are dividing the angle APO equally. So to divide that angle equally, let's say it gets to this point that we are calling B. So again, remember, the angle APB is the same as angle BPO, which is the same as half of angle APO, just like in the previous case. And so just like in the previous case, this is 60 degrees. This is 60 degrees. This is another 60 degrees. And so then we move on to the point where now I want to add a zero and a pole. The original, the original position of, remember at point 2 here, I'm just going to indicate at this point here, we knew we had a pole here for the plant, and was it there? No, it wasn't there. The pole was at, yes, the pole was somewhere here and down here because they were complex. And this point here was, this is -2. Okay. So to the left of -2, we need to put our pole and our zero. And we start with our zero. So our zero should lie somewhere here. So we can put our zero somewhere as long as it's to the left. So I don't even need to indicate this now. They just make this place look cluttered. But I know that it should be to the left of 2. So if we have the point here, if we have the point at 2, so let's say the point at 2 falls there. This is 2. We can have our pole at that point, and then of course our zero, our pole at this point, and then 0 at this point. So that point B cuts across the pole and the 0 equally. So this location here should be -P, and this is -Z. minus z. Okay? And then now we go ahead and indicate you have that, and you also have this. So you need theta p, and you also need theta z. Then you can proceed from there, because remember, this angle here, our angle was 11.5 degrees. So if I divide that by 2, 11.5 divided by 2, I should get 6 point, is it even 6? It's 5. And then 5.75. So this angle here should be 5.75. This one should also be 5.75. So that the total angle between the pole and the zero is 11.5 degrees. So now, again, using the same method as I did, you can get what this angle is. Because you know this angle is 60, so you know this is 120. This is 5.75, so you can get theta p. So theta p would basically be, you're going to do this on your own now, should be 180 degrees minus 120 minus 5.75. That should give you theta p. Theta z should be, if this is 60, and this is 60, this is 5.75. So theta z should be 180 minus, in brackets, 180 degrees minus 65.75. Okay? So you find that, and then you obtain the location point P, and you also obtain the location of point Z. So please complete that so that we can have those, we can compare your solutions in the next class to ensure you're correct. So then now you need to find what is that position, what is that position, then what is, so you'll have to write for me what that is. Then you'll also have to get for me what K is from the magnitude condition. Then you'll have completed. You can also go ahead and obtain the position constant and the velocity constants, the ramp constant and the...
Excuse me, sir.
Yes.
I wanted to ask, I've heard you say that the angle that is formed from the design point to the origin is 60, being that we need the equilateral triangle to be formed between PB and O.
Yeah.
My question would be, in this case, where now you have the design point at minus 1.8 and J 2.4.
Yeah.
The angle, it's about 50 degrees. I don't know if that 60 degrees comes by an assumption that you'll be equilateral, or what exactly is the explanation behind that?
That's a good question. Actually, because this is a design, we do not have a very specific way of obtaining the accurate results. So the only way we can do that is to make the assumptions, as I have mentioned, of obtaining that equilateral triangle to help get us those angles. Now, those angles are not 100% accurate, but at least it adjusts our plant system so that we are sure that the position, or at least the shape of our root locus, is going to change, and it's going to ensure that it's on the left half plane. So yes, I agree that from a design perspective, this is not 100% accurate. Why? Because you can see we are making the assumption of using the equilateral triangle in order to help us obtain the other angles, okay? Because without that assumption, it will be very, very difficult for us. In fact, if you read books, you will see that they use algorithms. And remember, again, in algorithms, you put in your best case scenario. There's no very accurate result that can be obtained from this. It is a design. So it means it's a trial and error. If you read the book by Kay Ogata, you will see that it's a trial and error. So you suggest, you place in the value, you see how it looks like, then you suggest another value, and so on and so forth. But this method here, sort of, yes, it falls from the most accurate result, but the margin of error is not that wide. So that is why we are using it in class here for this kind of design cases. But in real sense, if you now want to pursue this further, you will then have to use tools like MATLAB or some other algorithms that will help you obtain these design specifications. But when we are to do it manually, then like I told you, remember, even in root locus, if we are to do it manually, we cannot get the exact root locus. We are actually just sketching and refining our sketch. But if you use a tool like MATLAB, then it comes out to be as accurate as possible. So the same way here, in obtaining our poles and zeros for our design, we are actually estimating. We are estimating. But if you had used a tool, the results would not be very far off, but at least we shall have obtained values that can make sense. I hope that is clear.
Yes, it is.
Yes, thank you. So please note that even in the root locus analysis that we did, plus the design that we are doing now, these are estimations because we are doing them manually. You must have seen by now that the sketches that we do, if you plot them in MATLAB, they look similar, but they're not the same. They're not exactly the same because we can't be as accurate as that when we use manual techniques. So this is a manual technique. That is why we are making the assumption of the equilateral triangle. But in real sense, you'll realize that this angle should be 50 something, but at least it's still close to 60. But in order for us to obtain these values, we have to go that direction. So please complete this so that I'm also going to complete it and see the solutions that I get. Then we compare them in the next class as we discuss the lag compensation. I hope that suffices for today. So I'll end the class here and hope that we can meet again. You'll decide whether you want us to do it online or physical. So the class rep will communicate that. Thank you very much, ladies and gentlemen. Have a good evening and goodbye.